Assalamu alaikum. Hello, everyone. Today we start a new topic, the topic of linear regression. Uh, so regression is a process of modeling a relationship between variables. So using one or number of input variables, you want to build a model so you can predict the value of a target variable from those inputs. Okay, so let's start with this example here. So assume, for example, here, let's start with this example and answer these questions, okay? Here we have this data set. We have two input attributes, okay, the student ID and the attitude, and we have one target variable, the score variable, okay? Now we need to calculate the correlation between attitude and score. Okay, and student ID here is an auxiliary variable. Okay, it's just for identification, so we don't really need it for any kind of analysis. Okay, so we will compute the correlation between these two variables, and then we need to see we need to answer this question: if attitude decreases, then score will increase. True or false? We need to check that. Okay, and the last question: if attitude of a new student is equal to 74 units. Okay. Then can you estimate his score before the exam using the correlation? Okay, so maybe let's start with the last part here. Okay, so given the correlation, the value of the correlation coefficient, okay, can we use that to predict the exact, can we benefit from the correlation coefficient in building relationships between variables? In fact, correlation coefficient can tell you only two things, okay? Can tell you if there is a relation, okay, how strong that relation is, and the direction of the relation. What I mean by the direction of the relation, let's say X is your input and Y is your target variable. So the direction means like if when X increases, Y increases, then the direction is positive, okay? There's positive correlation. If X increases, Y decreases, then there is a negative correlation. So correlation can tell you only these things, okay? So for example, here, look at this here. Like I added this example here. Two two relations here. Here, Y is equal to X. If you compute the correlation coefficient here, the persons are correlation coefficient, you'll find that R is equal to 1. Okay, they are perfectly correlated here. There's a perfect linear relationship between Y and X. Okay. Now here, Y is equal to 10X plus 70. This is also perfect linear relationship. So if you compute the correlation coefficient, you will find that its value is also equal to 1. So R is equal to 1 here as well as here. Okay. So with that, we conclude like when R equal to 1, that doesn't really mean Y is exactly equal to X. I cannot predict Y from X. Given a value for X, I cannot tell what the corresponding value of Y will be. Because any perfect relationship will result in R equal to 1. So I don't know if Y is exactly equal to X or Y is equal to 10X plus 70, or in general, Y is equal to some beta 0 plus beta 1 times X. So I cannot really infer that information from the correlation. I can just infer that there is a relationship, and that relationship is positive or negative or whatever, okay? So these are the only things I can get from the correlation, okay? So in order to predict for a given value for X, we want to predict what will be the corresponding value for Y, then we need to build a model. Then we use regression. Yeah, regression, yes. When we build a model, then we will be able to plug in the value of X and compute the estimate value for Y, as we will see later, okay? So now let's look at the correlation between these two, okay? And see, answer the second question here, okay? So here, what we are doing, we are loading the data file and we're building, creating a data frame from that. Here we are dropping student ID because, as I said, it's an auxiliary variable. So we're dropping that and we compute the correlation between the remaining two attributes here, the attitude and the score, okay? And that's it. So when we run this is what we get here, okay? So this is the correlation matrix. So this is the correlation between attitude and score. So there is very high, very strong correlation, and it's a positive correlation. As attitude increases, score increases. Okay, this code here is just like to access correlation.log. We pass these indices, so this is like this index. So in row Y is defined by attitude and column defined by score. So this we are printing out this one. Okay, so there is a strong correlation between attitude and score, and it's positive correlation. So when attitude increases, score increases. So we answered these questions. Okay, so then the second one, the answer would be false, because actually the direction is positive, not negative. And as I said, if the attitude of a new student is 74, using the correlation, we cannot predict what will be the value of the score. Okay. As I said, the correlation can only show the strength and the direction of the relationship. Okay. Now, so I added actually this here to actually emphasize more onto this correlation and scatter plot, because they are important towards building a model here. So I created these variables here. Okay. The first variable is, I added a new variable, a new column. The value here is just the square of the original attitude attribute. Okay. That's just the square. Here it's a linear relationship. So a new column that is nothing but 2 times the value of attitude. So like there is no here intercept, there's no addition, just multiplication. So the intercept value is equal to 0. So this is a perfect linear relationship. Okay, even when you add a constant, it's perfect linear relationship. Any relationship like this, it's a perfect linear relationship. Okay, where y is equal to beta 0 x plus beta 1. Okay, sorry, beta 0 plus beta 1 x. So just to keep the convention. Okay, so here another column that is log. Okay, log attitude. So I just take the log, okay, of every value in attitude times 10 plus some noise. Okay, so just in average, it's a log relationship, but with some noise. Okay, with some noise that is coming from the normal distribution. Okay, and then I generate this this code from using like the elements of this are normal values following the normal distribution. Okay, that's a new column I add. Okay, so here like the values are following, like it's a random variable. The distribution is normal with mean 0 and standard deviation equal to 1. By default, if I don't pass those information, then the mean will be 0. Okay, and then I take the square of that. That's another feature. That's another column. Okay, so then here we actually I drop the student ID and I compute the correlation between all of these. Now let's look at this. So attitude, now this one was linearly related to attitude. Okay, it was perfect linear relationship. This is 2 times the attitude. So as we can see here, the correlation is equal to 1. Okay, but also for the square and the log, the correlation is so high. Okay. Okay. In general, persons R correlation, in general, it may fail to capture the non-linear relationships. Okay. But sometimes it does. Okay. So it doesn't always fail here, because all of the values are in the positive side. Okay. As X increases, Y increases. So you see like the correlation value is so high here. Okay. So though, as I said, the relation here is not linear relation, but we are capturing that relation here. So in fact, when you like, don't always look at the correlation itself without looking at the scatter plots. So correlation is good, but you always need to also look at the scatter plots to know the exact relationship between any two variables. Okay, are they when the correlation is high, it could be like very like an average. It's a linear relation. If it's 1, then it's a perfect linear relationship. Yeah, but if it's high, but it's not exactly 1, then maybe you need to look at the scatter plot to decide. Okay, to make sure like to see if there's a really in average there is a linear relationship, or it's some kind of other relationships. Okay, So as we can see here, for example, okay, let me take this here, this random, the one here. This is, I created this and I take the square of it here, right? So if you look at this, the correlation between uh, this random column and the square of it is very low. Okay, though there is very clear relationship here, but the correlation value is very low. Okay, this is nothing but the square of that. So the correlation here is not capturing that this is the square of that, because actually here it's a normal distribution. So the center is zero, the mean. Okay, so there could be positive and negative values, and here it's biased toward the negative because for this specific case there were more samples in the negative side versus the positive. Okay, so if you repeat this again and again, and you take the expected value of those, if you repeat this like for large number of times and take the average, this will go to zero because it's actually centered around zero. So as I said, if I run it, for example, again, let me run it here. I didn't run these cells, right? I may get different result. Okay. So for example, here, you see, it's a different result. And if I run it again, okay, so I get different results. So for example, here it's very high. So it's more in the negative side, okay, because there were more samples there. But in general, here, it could be like I mean, in this case, the correlation is not really like you cannot rely on correlation to capture the relationship between these two variables. So if you look into, so when you see like the correlation between two variables is very low, then look at the scatter plot to confirm that result. Okay, if you look at the scatter plot and you see the points are all over the places, then these are uncorrelated because for a given value of x, y can take any value randomly, then they are uncorrelated. But if you see some kind of pattern, then maybe there is a relationship, but it's not really a linear relationship, okay? That's something I wanted to mention. So for example, here, log here, okay? So if you look at the relationship between attitude and log, it's very high because it's in the positive side. All of the values are, so it's very high, but it's not linear. That's something, as I said, you always need to confirm. Here, it's very high. If you go to build a linear model, then maybe you run into a problem because you relied that correlation is very high, then these are two linearly related. Let me go and build a linear model. You build a linear model, it will not perform very well because the relation is not actually linear. The relation is concave, okay? It's a log relation. So then if the correlation is high, go and look at the scatter plot before you come up with final decision. Okay, and I will talk more about this later on when we come to the case we will have many input features. Okay, we want to predict the value of a target variable given a number of input features because there are many things we need to talk about here, how you look at the different features and the relation between them, as well as the relation between the each feature and the target one. I will keep that discussion to sometime later, okay? Let's continue now. As I said, you can plot the scatter plot here, and this is what I did. For example, here, here. So the score versus attitude, okay? So it can be approximated by a linear relationship. So then that's good. We can build a linear line, okay, or regressor to estimate the relationship, or to build an estimation for the relationship between attitude and score, because the relationship here can be approximated by line. Okay, so let me show you the log1 here. Okay, so here the correlation was high, but if you look at the figure, it's going to be something like this. Okay, so the correlation is high, but from the scatter plot, you can tell like this is actually, here there are not many points, okay? If there are more points, it will become more clear, like it's going to flatten here, okay? So linear, if you take it as a linear relationship and you build the line, you would do bad job for the points that are coming here, okay? So that's why you always need to look at the scatter plot after the correlation, okay? So this is a perfect linear relationship, okay? Because this is the value of this is nothing but 2 times the value of attitude. And this is perfect relationship, okay? Linear relationship. Okay, that's enough as an introductory and explanation to the benefits of correlation and scatter plot and how do you use them. Okay, now back to regression versus correlation. As I said, correlation may indicate whether two variables are related or not, but you cannot use it to predict one from the other. Regression, we can, okay? So here we will focus in linear regression, okay? So for example, let's look at this example here. This is X and this is Y. These points here, the black points are the values of Y for a given X. For this X, this was the exact value for Y for our training data set, the data that we're gonna use to build the model. Okay, so for this data, we have the value of X and the corresponding Y. And from this, we need to come up with a line that can actually relate Y to X linearly. Okay, so here we have those black dots. These are the exact points. Okay, for this X here, this was the exact value, the actual value of Y. For this X, this was the actual value for Y. Okay, we want to come up with a line. So we want to actually estimate that relationship as a linear relationship. As you can see visually here, maybe this is the line that does the best, right? Among all lines you can come up with, this seems to be a reasonable one, all right? So how do we end up choosing that line? Okay, so then actually what we need to do is we need to consider some error function, and we need to find, okay, first of all, the line is defined by what? This equation, right? Beta 0 plus beta 1 x, right? So then we need to, do, beta 0 is the intercept, beta 1 is the coefficient of the input feature, okay? Or the slope of the line, okay? So let's focus on the line. Okay, so beta 0 is the intercept and beta 1 is the slope of the line, all right? So then any line is defined by these two variables, right? The intercept and the slope, okay? So among all lines that I can come up with, among all choices for beta 0 and beta 1, we need to choose the one that minimizes this error function. This is a good error function to use, okay? So what kind of error function? This is the difference. This is the error, right? This is, so look at this here. Beta 1 xi, for a given xi, for a given input sample, we compute what we call yi hat, okay? So the estimate of actual yi. So this is the estimate y, and this is the actual y, okay? So take the difference between them, square it for every point, and you sum over all the points. You can consider the sum as well as the average. So the minimizer, the beta 0 and beta 1 that minimizes the sum of the square errors is the same as the ones that minimizes the mean of the square errors, because this is actually constant. You always getting the minimum value for this one. So let me come back here to the figure. This is actual y for point I here. This assume point I is here. Okay, this is actual y, and this is the estimated y. Okay, the y projection of that point into this line. So we want to, like, we take that difference square for every point, and we sum over all the points, and we take the average. That is some error function we want to minimize. We want to find the line or the beta 0 and beta 1 such that this error function is at its minimum value. Okay, so this is a good function to consider. In fact, if these errors follow the errors, like the differences between the actual and the estimated y follow normal distribution, then this is known as the maximum likelihood estimator. If you don't know that for now, that's fine. Okay. Another choice for the error function is the absolute errors, right? The sum of the absolute errors, right? So you can take the difference between this, the actual and the estimate, take the absolute of that, and you sum all the absolutes, or you take the average as well. Okay, that's another choice. Okay, but this one has many nice properties. Besides, it's the maximum likelihood estimator of if the errors are normally distributed. It has also some other nice properties that we will talk more about them later on. It's strictly convex. In other words, there is only one unique global minima. It's smooth and differentiable everywhere. These properties, we will talk more about them later on, but these properties are very, very useful when it comes to the way we solve this problem, especially if you have a large number of samples and large number of features, okay? So we will talk about that later on, okay? Let's keep it simple now, and I don't want to go ahead of the slides, okay? The goal here is to find this line, the line that minimizes which is defined by beta 1 and beta 0. Beta 1 and beta 0, that minimizes this error function. So we need to make sure that we come up with a line where the sum of the square errors or the mean of the square errors in the training data set is minimized. Okay. So as I said, this is the equation of the line. Okay. It's beta 0 plus beta 1x. Now this problem here, okay, it has a closed form solution. Okay. It's simply, we can very simply solve this, like take the partial derivative with respect to beta 0 equate to 0, and take the partial derivative of the error function with respect to beta 1 and equate to 0. Then you can solve for beta 0 and beta 1, and you can come up with this closed form solution. Okay, where beta 1 is equal to the correlation coefficient times the standard deviation of y divided by the standard deviation of x, and beta 0 is equal to y bar minus beta 1 x bar, where y bar is the mean or the attribute y, mean of these values. Okay, and x bar is the mean of the input feature, this mean of these values. Okay, so yeah, if you, as I said, if you take the partial derivative and equate with respect to beta 0 and beta 1 equate to zeros, then you can actually end up having this. Okay, you have two equations with two variables. With some simplifications, you end up having this. Okay, so that is the closed form solution. Okay, yes, back to the example here. As I said, we plot this. We found that it can be approximated by, so we are back to the example here. Okay, sorry. So this was general explanation. Okay, and here back to our example here. Okay, so here we have the scatter plot between attitude and score. Okay, we computed the correlation. We found the correlation is very high. We plot the scatter plot. We found like it can be approximated by a linear relationship. There will always be error. Okay, because as I said, it's approximation. Okay, so there will always be error. Okay, so we want to come up with a line. Okay, so a line that passes maybe this way. Okay, is the best, right? Okay, so we're gonna find that line. Okay, so simply we can use these two equations to find beta 0 and beta 1. We have all the values here, right? For the variable x and y, we can compute the standard deviations, we can compute the x bar and y bar, then we can plug in, so we can compute this here. Okay, beta 0 and beta 1 for this specific example here. Okay, and here we got beta 0 and beta 1. Beta 1 is equal to 6.93, and beta 0 is equal to minus 330. Okay, that is using like computation. We can do it with Python as well. So from scikit-learn.linear model, we import linear regression. Here we create an object for that regressor, and here we fit that in our data. This is our input variable x, and this is our target variable y. So here, one thing I want to mention here, here we pass this argument here for when we are creating the regressor, fit intercept is equal to true. Okay, by default is equal to false. Okay, so here so we are actually considering the intercept. Okay, so we don't want, so when it's false, what's that supposed to mean? So it's supposed to mean that we are interested in only the lines that pass through the origin. Because when intercept is equal to false, that means beta 0 is equal to 0. When beta 0 is equal to 0, then we are actually saying we need to find a line that approximate this relationship, but among all the lines that pass through the origin, find the best. Okay. Now, for example, if these points are shifted to the right somewhere here, then all the lines that pass through the origin will do bad job here. Okay. Or if the points are here, for example. So then I would say always choose this to be true, because this is more general. If the one that passes through the origin is the best one like is the best linear estimator for your data, then it will be chosen. Okay, you don't need to stick yourself with only the ones that pass through the origin. So I would say make this always true, because it's more general. If that's the best solution, if the one where beta 0 is equal to 0, then you will choose that one already. The model will choose that one. And that's it. So here we define the regressor, and here we fit that in our data. This is our input feature x, and this is our target variable y. And we can actually we come up with the value for beta 0 and beta 1. So beta 1, which is the slope, is equal to this, and beta 0 is equal to that. The same values we got when we plugged in the input data into the closed form formula. Okay, so here the one how do we access the coefficient and the intercept here? Okay, so the coefficient is the slope, is the coefficient of the feature, the weight of the feature. Okay, so we access it like we call this function. Okay, sorry, this we retrieve this attribute or property from the regression. So cof underscore. Okay, if I don't pass 0 here, okay, if I don't index it, okay, it will pass it. It will return it inside brackets because there is only one. It will return because this is more it's very general. If I have more features, then it will return all the weights. Okay, all the coefficients. But here, because there's only one coefficient, so it returns that coefficient inside brackets. Okay, so if I do it this way, then I'm accessing that element. Okay, so I'm accessing the first element, which is the only element. Okay, so this is the slope or the coefficient of the input feature. And when we call dot intercept underscore, so we're returning the value of the intercept. Okay, so here this is like comma 2, so because we're passing 2 around, this is just rounding. Okay, so considering only 2 digits after the decimal point. Okay, and round the last one to the nearest integer. So that's only for rounding. Okay, so that's it, very simple. So we import the linear regression module, we create the regressor object, and we fit that in our data, and then we can print out the coefficients and the intercept. Okay, now if a new participant with positive attitude of 78 is taking the exam, what will be the estimated score? Simply, we plug in 78 in as our input X here, 78. And then now we have already the value for beta 0 and beta 1. So beta 1 times X plus beta 0. So we have the prediction. Or when the attitude is 78, we have the estimate value for the score, Y hat. Okay, so we are able to estimate the value of the score for a given value for attitude. Okay, so how do we do that with Python? So here's a new X that's equal to 78. So we call the function predict, reg.predict, and predict always takes the input as a column, 2D array with one column. So that's why we are reshaping it as one column. Okay, so we pass 1 here and -1 here, whatever that like depends on the number of elements. Okay, so we are shaping that to one column, and then we are passing that to predict. Then we can print it out. Okay, and this is what we get. So for 78, okay, the estimated score for a student with attitude 78 is equal to 210.3. Okay, so it's inside the brackets, but it's only one because this is more general. It can take more than one input here. Like input with more, like for example here, let's take this one here. So there are, we want to predict, so these are new points, okay? And we want to predict or estimate the value for the score for each one of these. So for each one of these given input attitudes, okay? So we call the function predict, and we reshape this as a 2D array with one column, okay? And then we pass it to predict, then it will return the prediction for every one of these. These are the input variables, and these are the predictions for, or the estimate for the target variable Y. So this is for the like a student with attitude 78 equal to 78. The estimate value for the score is equal to 210. Okay, 210. So I think 68 was one of the input points. Okay, if you go back, so the estimate here was 140.97. If you come here, 68. Okay, so it was here. The actual one was 143 here in the data. Okay, so here the estimate is 140.9. So there will always be an error. Okay, there will always be an error.